In the previous few videos, we were mainly focusing on the matrix and vectors, this kind of a data structure, this kind of a containers that allow us to solve various kinds of problems. Right? We looked at how to do matrix multiplications. We looked at um, how to use matrix multiplication to solve linear systems by using the steepest descent method. We looked at various ways of manipulating matrices and vectors, right? So all those things are related to something that we call data structure, which are basically the algorithms and operations that we can apply on the containers of data, right? Um, let's um, if we sort of look back about what exactly we have learned so far, right? We started by just looking at how to use the button clicks, how to use the graphic user interface provided by Matlab to manipulate data, to import data, manipulate data, making plots, right? And then we moved on to study some of the basics about flow control. Right? We looked at how do we actually write loops by using the for statements. We looked at how to do the branching structure using the if, else, if, else, and this kind of a construct, right? And um, and then we moved on to talk about matrices and vectors, these kind of data structures, right? And now let's get back to talk about flow control, right? Let's get back to talk about flow control. So at the beginning of the semester, I was saying that almost every kind of a programming language has just the two components. One is called data structure, the other one is called flow control. Right? This is a extreme simplification about the reality, but if you look at the roots, or if you look at the essence of every kind of programming language, data structure and flow control are like the most fundamental pillar of every kind of a programming language, right? So what we have been doing is to actually study these two things in some kind of a alternating fashion, right? We're doing it in a staggered way. So we talked a little bit about flow control, and then we talked a little bit about data structure. And now let's get back to talk about a little bit more about the flow control, right? After we have finished talking about this part of the programming language, this part of the Matlab, we will be able to actually improve our function for solving linear systems using the steep descent method, and we will also be able to sort of solve a wider range of problems, right? And in this part of the discussion about flow control, we're going to look at some kind of combination of loops and conditionals. So in the last segment about flow control, we're talking about the loops and the conditionals as two separate things. Right? The loops is based upon the for construct. Right? You have to specify a range of iterations. You have to sort of specify the number of iterations that you want to execute for a particular for loop construct. Right? And then when we talk about the if, else, and this kind of construct, it's purely just a branching structure. Right? It purely just determines what's going to be the code block that's going to be executed based upon one or two conditionals, a few conditionals, right? That's going to be evaluated to either true or false depending upon the data, depending upon the result of those evaluations. Right? So here let's talk about another loop construct that's going to allow us to combine iterations with conditionals, right? So this kind of construct is different from, for example, putting a for loop block inside of a if, else, if branch, right? It's not different. It's not the same like that. And it's also different from using a if branch inside of a for loop. It's not done like that, right? The thing that we will try to actually construct is something that's called a while loop. A while loop. one of the drawbacks of the for loop is that you have to sort of explicitly specify the total number of iterations. Right? But sometimes we don't really know how many iterations are needed in order to achieve a goal. Right? The goal is kind of specific, it's given, right? Suppose we want to achieve a certain accuracy for our solution, that kind of thing, right? This kind of thing is given, but we don't really know how many loops are going to take, how many iterations are going to take to reach that particular accuracy, that kind of thing, right? And in this kind of situation, the while loop becomes extremely useful, because the condition for terminating, or the condition for continue executing the loops is based upon a conditional. Right? If the conditional is true, is evaluated to true, then the loop is going to keep executing. And then if the conditional evaluates to false, then it's going to stop executing the loops. Right? And if we think about our linear system solver based upon the steepest descent method, for now our implementation actually our function actually requires us to actually input the number of iterations, and that number of iterations is kind of arbitrary for now, right? It's a fixed, it's a very large fixed number. For now, in all our examples, we're giving the input 10,000, right? 10,000. We're giving it a fixed number of 10,000. But how do we know? How do we know if it's actually enough number of iterations, or is it not enough number of iterations, right? So if the number 10,000 is too big, then we are basically just wasting computing resources to do some kind of unnecessary calculations. But if the number is not big enough, then we haven't actually reached the accuracy of our required the required accuracy of the solution, right? So how do we actually determine the total number of iterations that's needed in order to reach a certain criteria intelligently, based upon certain conditional, right? And at this point, the while loop becomes really important, becomes really convenient. So we're going to look at this particular exercise that's taken from our textbook, right? So we're going to use this particular exercise to motivate our discussion about the while loops. So what exactly is this exercise about, right? It's about the Newton's method for solving or finding the roots of particular equations, right? So let's look at the description of the problem. The Newton method is used to determine the value of x that makes fx smaller than t0, which is about 0. Right? Which means what? Which means it looks like a really complicated expression, right? But in principle, it's actually quite simple. It's actually finding the x that makes fx as close to 0 as possible, right? So if you sort of visualize the fx as a function, x is the horizontal axis and fx is the vertical axis, right? You're going to have a curve. And the Newton's method is for finding the locations, the x points, the x values at which the curve actually is crossing the horizontal axis, right? Those crossing points are called the roots of fx equals to 0, this kind of equation, right? If you try to solve the equation fx equal to 0, then Newton's method is one of those very popular techniques for solving that. Right? So the value of x is determined from the following formula, where x0 is the initial guess. So you start with some kind of an arbitrary initial guess about what the root could be, x0. You just start with some arbitrary value, x0, right? And then you just do this thing. So x1. So suppose 0 n equals to 0 now, right? So x1 is going to equal to x0 subtract fx0. Fx0 is what? It's the function fx evaluated at the location x0, right? And then divide f prime x0. F prime x0 is what? It's the derivative of fx with respect to x. And then this derivative is going to be a function of x also. It's going to be a different curve, but it's still going to be a function of x. And then you evaluate this derivative function which is denoted as f prime here, at x0, right? And you do this subtraction, and then you get x1, right? And then you bring x1 to the left-hand side. So x1 subtract fx1 divided by f prime x1, and then you get x2, and then you keep iterating, right? And at a certain point, once you reach a certain number of iterations, you will find that fxn, suppose n equals to like some number, right, is going to be very, very close to 0, right? And in this equation, the prime denotes the derivative with respect to x. And the value of n is a function of the tolerance t0, which is a very small value. Right? T0 is supposed to be very small. How small? Depending upon the problem, right? Maybe 10 to the minus 10th power, 10 to the minus 20th power, that kind of thing, right? Very small number. And the choice of x0. So suppose you picked an x0 that's already very close to the root of the function, then you could just take like a couple of iterations, then you are gonna get to the exact solution, right? But if you picked a value that's kind of very far away from the root, then you could take like a lot of iterations to actually reach that particular root, right? So write a function that obtains the value of x when fx equals to cosine x plus sine x, f prime x equals to minus. So if you look at this particular function, the derivative can be evaluated analytically, right? So if you know calculus a little bit, you know how to actually compute the derivative, right? So f prime x equals to minus sine x plus cosine x, right? So if you don't really know calculus, if you don't really know how to actually take a derivative, it's also okay, because Matlab actually has a symbolic toolbox which is going to allow you to evaluate derivatives analytically, right? It's going to do this kind of evaluation for you, right? We haven't actually had time to talk about the symbolic toolbox yet. If we have time, we can talk about that, right? It's quite useful, right? And this kind of a computer algebra system, which allows you to do this kind of a calculus analytically, can be quite useful. And another software that allows you to do this kind of a computer algebra or this kind of derivative analytically or using a computer is called Mathematica, right? It's a software that's kind of comparable in terms of functionality. It's kind of comparable to MATLAB, but it's actually, it has a shorter history than MATLAB, right? So MATLAB was kind of has been around for like close to probably more than 30 years, close to 40 years, probably. But Mathematica is newer. It's a newer software. It's been around since probably late 1980s or early 1990s. So it's like 10 or 20 years later than MATLAB. So, but Mathematica is also a very well designed software. It has beautiful interfaces and it has strong capabilities, but it's just not as popular as MATLAB at the current stage. But maybe it's going to change in the future. Right. So in this particular case, for this very simple function, you can compute the derivative very analytically. So f prime x is going to equal to minus sine x plus cosine x, right? And then it's giving you a suggested guess number that's equals to 1.5. And then it's giving you a suggested tolerance that's 10 to the minus 8, right? And then what you want to do is to write a function that's going to have this kind of output. So have the output of the program displayed to the command window, the various quantities as shown below. So at x equals 0.356195, fx is going to equal to this number after 4 iterations. So that's going to be displayed by the computer program that we're going to write, right? So x0 started with 1.5, but at the end of the execution of the program, x is going to have a different value, right? And when x equals to this particular value, fx, which is this particular function, right, is going to have a value that's very, very close to 0, right? 10 to the minus 16th power. So this is sort of the scientific notation in Matlab. It's some floating point number, and then this e, this letter e, represents multiplied 10 to the something power, some power, and this power is given behind the e. So if it's minus 16, then it's 10 to the minus 16th power. That's like 16 zeros in front of this leading 1, right? Or 15 zeros, I think, right? That's a very, very small number. And then it also has to display the total number of iterations. So n, how many n? What's actually the n that allows us to actually reach this particular x, right? So that's the number of iterations. So after like 4 iterations, after just 4 iterations, we go from this sort of arbitrary guess to the true value, to the correct root, right? So it's 4 iterations is not really that many. It's just that's probably just because the starting value is not too different from the root, right? So that's the goal. So that's the thing that we will try to solve. We're going to try to implement a Matlab function to solve the Newton, to implement the Newton's method for finding the root of a particular function. So if you look into Wikipedia, it's got a quite nice graphical representation about the Newton's method, how it actually solves the problem, right? So y equals to fx, that's the red curve, that's the red curve here, right? So it looks like quite a smooth curve, right? So that's fx. Then where exactly is the root of this particular function, right? The root of this function is when fx equals to 0. So y equals to 0, right? When y equals to 0, that means that the red curve must cross the horizontal axis, x, right? So the true root is supposed to be this red spot, right, where this red curve is crossing the horizontal axis. At this particular point, fx is going to equal to 0, y equal to 0, right? So what we need to do is to actually find the horizontal axis, the horizontal coordinate of this particular red spot, red point. The horizontal coordinate of this red point is pretty much just this particular length, right? Goes from 0 to this particular location, right? So that's the goal. We need to actually find the horizontal axis of this red point, right? So how are we going to solve it? How are we going to solve this particular problem, right? The Newton's method works like this. So you start with some kind of arbitrary guess, x0, right? And then you draw a vertical line. And then you draw a vertical line to cross this red curve, this fx function, right? So at this black spot, at this black point, the y coordinate of this particular black point is going to be fx0, right? That's the y coordinate of this particular black spot, right? And then at this point, you're going to draw a line that's tangent to the red curve. A tangent means what? A tangent means every point on this straight line is not going to go above this red curve. Every point is on this straight line is going to be either at or below this blue curve of this red curve for this particular example. I mean, right? If the function is like a convex, then the tangent line is going to be a straight line with every point that's kind of equal or above that convex line, right? But for this concave line, it's going to be this kind of a tangent line, right? And this tangent line, this straight line, is going to cross the horizontal axis at a certain location, x1. Let's call that location x1, right? And this x1, this location x1 can be computed. So how do you actually compute it, right? How do you actually compute it? How do you actually compute this crossing point, right? Don't forget, you are drawing a straight line that's tangent to this particular red curve at this particular point, right? So it means what? It means the slope of this particular straight line, this blue line, blue straight line, is going to be identical to the slope of this red curve at x0. The slope of the red curve is actually given right? It's f prime x. So the derivative actually gives you the slope, right? So all you have to do is to actually compute f prime at location x0. Then you're going to get the slope. And that slope is the slope of the straight line also. This blue straight line, right? So you can, so the slope of this blue straight line is going to be f prime x0, right? And then you also have another way of computing the slope of the straight line, right? What's actually the slope of the straight line? It's this length divided by this length, right? This horizontal length is x0 subtract x1, right? And then this vertical length is what? Is fx0, right? So fx0 divided by x0 subtract x1 is also equal to the slope, right? Right. So fx0 divided by x0 subtract x1 is also going to be equal to f prime x0, right? And these two different ways of computing the slope should give you identical slopes, right? And this identity, if you rearrange that particular identity, you're going to get the Newton's formula, right? You're going to be able to actually solve for x1. x1 is going to equal to x0, right? Subtract fx0 divided by f prime x0, right? If you don't believe my derivation, you can try to rearrange this particular equation, right? So the length here is x0 subtract x1. So if you move x1 to this side, x0 subtract x1, right? And then the vertical length is fx0, right? So you move the whole division to the left hand side. So it becomes x0 subtract x1 on the right hand side, and then fx0 divided by f prime x0 on the left hand side, right? So at this point you can just multiply f prime x0 on both sides, right? And then divide x0 subtract x1 on both sides. Then you will be able to recover that f prime x0 actually equals to fx0 divided by x1 x0 subtract x1, right? So you will be able to actually recover what I was just saying, right? So that's after one iteration, so you get to x1, and then you keep doing that. At this location x1, you evaluate both fx1 and f prime x1, and then you draw another straight line, right? Draw another straight line. That's tangent to the red curve and passing through the location x1, right? And then this green straight line is going to intersect with the horizontal axis at location x2, right? You can sort of see x2 is already very close to this red dot, right? And then you just keep doing that until you actually reach this red dot, right? After a certain number of iterations. So how do we know we have reached this red dot, right? So the conditional for us to actually evaluate if we have reached this red dot or not is actually the tolerance, right? The tolerance. So here it's actually specifying the tolerance, right? It's smaller than 10 to the minus 8. So if fxn, the value of the function evaluated at xn, has reached this tolerance, then we say that xn is kind of accurate enough, right? And then we just stop the iteration, right? And then print out the number of iterations, the n, right? So that's the basic strategy for us to actually solve the problem. But in order to actually write this particular function, we will need to understand two things. One is the while loop, right? That's sort of the focus of this particular video, and maybe the next one. And another thing that we need to understand is something that's called a function handle, right? So here we are having a specific form of the fx and f prime x, right? But I suppose fx is kind of general. You don't really know what's going to be the form of the function, right? And then what you want to do is to actually, for the function that implements the Newton's method, you want to have fx and f prime x as the input to this function that implements the Newton's method, right? So what's actually going to be used as the input is not going to be a data. It's going to be a function. It's not some kind of data. It's not some kind of number. It's a way, it's an algorithm for computing the fx, right? So you are using a function as the input to another function, right? And in this case, we will need to understand what exactly is the thing that's called a function handle. Matlab is actually a functional programming language, so it allows you to actually pass around functions or implementations of functions around just like a piece of data, right? You can use that function handle as the input to another function. So we will need to understand these two things before we can actually implement or solve this particular problem. So here let's look at the while loop first, right? So how do we actually implement the while loop, right? So let's look at this kind of a motivating example. It's a lot simpler than Newton's method, but it's a good example for us to look at the while loop. This kind of a syntax, right? Again, it's an example taken from our textbook. That's example 4.13. It's talking about the convergence of a series. So let us determine and display the number of terms that it takes for the series Sn equals to a summation with an index of small n. Small n goes from 1 to capital N. And the terms that we are trying to sum up is 1 over n squared. Right? And then for this particular series to converge to within 0.01% of its exact value, which is when big N equals to infinity, it's supposed to converge to pi squared divided by 6. Right? So when big N equals to infinity, which means that we have to sum this particular term up to like infinity, right? But in practice, it's impossible. Right? But as long as we have reached like a 0.01% of the exact value, we can stop this summation. We don't really have to keep iterating anymore, right? So the criterion for stopping the summation is what? Is the summation result is within like 0.01% of the exact value, right? And that's a conditional. We can write that as a conditional, right? So if the result of the summation reached this kind of accuracy, we can stop the iteration, right? And we should keep iterating when the result of summation is not accurate to this kind of precision yet, right? So the conditional for keep iterating is just the opposite of the conditional for stopping the iterations, right? So let's look at how we can actually write this particular program, right? So I'm gonna write a new script, and then I'm gonna call it convergence of a series, right? And the series that we're trying to actually compute is just this this particular example, right? And this thing actually involves the summation, right? So how do we actually sort of do this kind of summation using a loop, right? How do we actually use this summation as a implement this particular summation as a loop, right? So the first thing we're gonna do is to actually come up with something that's called the accumulator. Let's define S, capital S, and it's gonna have an initial value of 0. So before the loop starts, capital S is gonna have the number 0 in it, right? And then as the loop actually continues, we're gonna accumulate or add those terms, 1 over n squared, those terms to the accumulator. So for the first iteration, when n equals to 1, so small n goes from 1 to capital N, right? So we don't really know how large the capital N should be in order to actually reach this kind of accuracy, right? But later on we can print out the capital N when the loop actually finishes, right? So let's look at the syntax first, right? the while loop is started by this keyword while, right? So as soon as I type while or small case, then you're gonna see it turns blue, which means it's a MATLAB keyword. So it's one of those keywords, one of those 50 keywords used by MATLAB for its grammar. Right? And then what's supposed to be behind this particular while loop, while statement, right? while keyword, right? What's supposed to be behind it? It's supposed to be the conditional for keep iterating, right? So every while loop must be closed with the keyword and, right? And this conditional that's following the while statement will be evaluated for every iteration. So when after all the statements that's in between is executed, MATLAB is going to come back to the beginning and reevaluate this conditional and see if it's true or false. So if the conditional is evaluated to false, then it's going to jump back to the end and then stop the iteration. But if the conditional is evaluated to true, then it's going to keep iterating. So what's going to be the conditional for us to keep iterating, right? Within 0.01% of the exact value, right? And then what's the exact value? It's pi squared divided by 6. So let's define another value that's called S exact. That's pi squared divided by 6, right? That's the exact value. And then the conditional for keep iterating is that it's not within 0.01% of the exact value. So there are two things that we have to be sort of aware about, right? What does it mean to be within 0.01% of the exact value, right? It means that the value that's inside of the accumulator S can be either bigger or smaller than the exact value. It doesn't really matter whether it's bigger or smaller, right? As long as the difference or the relative difference is 0.01%. Right? That's our conditional. Right? So it doesn't really matter whether S is bigger or smaller than Sn. Then how do we actually evaluate the difference, right? If we just use S, subtract S exact, then this number could be either positive or negative. It doesn't really matter, right? It doesn't really matter because it says within, so it's possible to be bigger than S exact or smaller than S exact, right? If this kind of a positive or negative thing doesn't matter, then we can just use the absolute value of it, right? We can use the absolute value of it, right? And then another thing that we have to pay attention to is that it's a 0.01%. A percentage is usually used to evaluate the relative difference, right? So this subtraction gives us an absolute difference. It's not a relative difference. So how do we actually get the relative difference, right? We have to divide it by S exact, right? So if this thing, this is going to be the absolute relative difference. It's going to be the absolute value of the relative difference, right? And if this thing is larger than, so 0.01%, 0.01%, right? Percentage is what? Percentage you have to divide by 100, right? That's going to give you the actual floating point number, right? So when this particular criterion is evaluated to true, then we want to keep iterating. And when this conditional is evaluated to false, then we want to stop the evaluation, right? We want to stop the iteration, right? So two things that we have to pay attention to. It looks like a really simple sort of sentence, right? Converge to within 0.01% of its exact value. But in terms of the code, there are two things we have to be careful. Within means what? Within means absolute value, right? convert it to a programming language. You want to take the absolute value, and ABS is the MATLAB function for taking the absolute value. And then it's a 0.01%, right? So it's a relative difference. So you have to do this division, right? And then another thing that you have to pay attention to is this larger than, right? This is because the conditional here listed here is not the conditional for stopping the iteration. It's the conditional for continuing the iteration, right? And then what's going to be the body of the loop, right? So S has to be equal to S plus something, right? What exactly is this something? It's 1 divided by n squared, right? So what exactly is n? What exactly is n? What exactly is n? Right? N is this kind of index in the summation, in the mathematical summation, right? N goes from 1 to capital N, right? So when n equals to 1, so it's 1 over 1 squared, that's 1, right? And that's actually the first term inside of the summation. What's going to be the second term, right? The second term is going to be when n equals to 2, right? 2 squared, that's 4. So the second term is 1 over 4, right? And then what's going to be the third term? The third term is going to be 1 over 9, right? So it's just going to be like that, right? So we need an n. We need an n. But in this side of this while loop, we don't really have an n. We don't really have an n, right? So let's define n. So n is going to start with 1, right? So 1 divided by 1 squared, that's 1. So for the first iteration, n is going to equal to 1, right? 1 squared, 1. 1 divided by 1 is 1, right? 1 plus, for the first iteration, capital S equals to 0. So 1 plus 0, that equals to 1. And this 1 is assigned back to the accumulator S, right? So that's for the first iteration. And then if the second iteration needs to be carried out, right? And then S is going to have a value of 1 now, right? So 1 plus 1 divided by 4, right? And then that's 1 plus 1/4, that's 5 quarters, right? 5 quarters assigned back to S, right? And then that's gonna keep going. That's gonna keep going, right? But the thing that we need to actually pay attention to is that inside of the while loop, we need to keep increasing n, right? So for the first iteration, n is 1, right? But if this conditional is evaluated true, then it's gonna have to execute the second iteration, right? But what's gonna be the value for n in the second iteration, right? For now, the code actually we have only 1 line. For the second iteration, n is still gonna be 1, right? There's no code for us to actually increase n by 1, right? So we need to actually add 1 more line. So this way we're going to increase n by 1, right? So for the first iteration, n equals to 1, so 0 plus 1, that's 1. 1 is being assigned back to S. And then we execute this line, right? 1 plus 1 equals 2. So 2 is assigned back to n. And then for the second iteration, n is going to equal to 2 now. So it's 1 over 2 squared, that's 4. Capital S now has a value of 1. 1 plus 1/4. Right, that's 5 quarters. 5 quarters assigned back to S. And then n, we execute this now line. N equals to 2 plus 1 now. 2 plus 1 assigned equals to 3. Right, 3 assigned back to n. Right. So this way we can sort of keep iterating and keep increasing both S and n. Right. And then after the loop has finished, after this conditional has been evaluated to true, then this while loop is gonna stop. And at this point, we want to do a disp, right? Disp. Let's just say number of iterations to reach 0.01%, right? Num to str n. N is the number of iterations, right? Right. And then we can just execute this code. Let's call it convergence of series, So it took like 6,000, 60, 80, this number of iterations to actually reach this kind of accuracy. Right. So that's let's look at what S actually is. Right. It's 1.6448, and then what's going to be S exact? 1.6449. So yeah, that's exactly 1%. Right? That's exactly 1%. Right. And that's sort of the solution of this particular problem. Right. So if you look at the syntax of the while loop, it's actually quite straightforward, right? It's just composed of two keywords, while and end. The difficulty is actually in coming up with the correct conditional. That's going to go after while, go after the while statement, after the while keyword. Right? What's going to be the correct statement? What's going to be the correct conditional? Right? And in this particular example, we also looked at how do we actually use the so-called accumulator, right? N is the counter, right? But this S is the accumulator. So for every iteration, we're actually adding something new to the S, to the accumulator, right? N is just incremented by 1, right? So in terms of mathematics, this expression doesn't make any sense, right? Doesn't really make any sense. But in computing language, this equal doesn't mean the value being identical. It means assignment, right? You're assigning something on the left-hand side, on the right-hand side, to the container that's on the left-hand side, right? So you're basically replacing the value that's stored inside of the container, right? And that's convergence of the series, right? So now let's look at another example that's also going to allow us to to study the while loop, right? And it's also related to pi, right? So this one is called approximation to pi. So the following expression converges to 1 over pi when x0 equals to 1 over square root of 2 and y0 equals to 1 over 2. And the expression is like that, right? And n goes from 0 to 1 to 2. Right? So so yn plus 1 equals to yn multiplied with 1 plus xn plus 1. This whole thing squared, subtract 2 to the n plus 1's power times xn plus 1. Right? And xn plus 1 is actually computed from xn by using this particular equation. Right? And the right hand side is based upon just the xn. Right? So you can imagine what's gonna be the basic structure of the code, right? So you're gonna have an x variable, and that's gonna be updated for every iteration, and the updating formula is basically just like that. So previous values of x is used for computing the right hand side, and then the result of the calculation is assigned to the left hand side to replace the current value inside of the x container. Right? Once you got the current value of the x, you use that current value and use this particular expression to compute the next value of y, to compute the new value of y, right? And you also have to use the old value of y, right? So the body of the expression is going to be a lot more complicated than these two lines, right? Because we're going to have to evaluate both x, re-evaluate both x and y, right? And the expression is quite complicated, right? And then the conditional, what's going to be the conditional for us to actually stop the iteration, right? We shall show that the difference, that's the absolute value, so 2 vertical bars means the absolute value, 1 over pi subtract y4 is less than 10 to the minus 15, right? So now it's not the relative difference, now it's the absolute difference. It's the absolute value of these two values subtracting each other, right? And this absolute difference must be smaller than 10 to the minus 15th power, right? And this example is claiming that after just 4 iterations, we can reach that kind of accuracy, right? So that's y4, right? Because x0 and y0 are given, right? So 4 means just 4 iterations, right? So let's see if we can write a script to solve this particular problem, right? Approximation to pi, right? That's gonna be so we're gonna need at least 2 variables. One is x and the other one is y, and then we have an exact value that's 1 over pi. So exact y, let's call it y exact, right? Y exact equals to 1 over pi. And then the starting value for x and y is going to be, so x is going to start with 1 over square root of 2, right? So that's, we're using the Matlab SQRT function to compute the square root. And y is going to equal to 1 over 2. So in terms of mathematics, they are using this 0 and this kind of n, this kind of subscript to represent some kind of index, right? In the past, we have been using this kind of visual clue to come up with arrays, right? So what I was saying is that whenever you see this kind of subscript, you think about arrays, right? That's going to be the index used for indexing into arrays, right? But here, we are not going to use the array. We're not going to use the vectors or matrices as our data structure. We're just going to use a simple variable. The reason is because we don't really care about the values that we come up with for previous iterations, right? We just care about the values in the current or the last iteration, right? If that's the case, if we don't have to actually store all the values throughout all the iterations, then we don't really have to use a array or matrix to actually store all the intermediate values, right? We can just keep using the same container and just replace the values inside of those 2 containers for every iteration based upon those kind of updating formula, right? So here we are just using this kind of subscript as some kind of visual clue to indicate it's the loop index, right? And then let's write our while loop, right? Let's write our while loop. What's going to be the condition, right? What's going to be the condition for continuing the execution of the while loop, right? So it's actually telling us it has to be the absolute difference, right? So let's again take the absolute value function. And then that's the y exact. That's the 1 over pi. Subtract the current value inside of y container, right? And if this value is larger than 10 to the minus 15th power, larger than 10 to the minus 15th power, then we larger than or equal to, right? Because the condition here is less than. Less than means that it's strictly less than, right? So the condition for keep iterating is going to be larger than or equal to, right? And this is sort of the scientific notation in Matlab. So 1 to the e means 10, right? 10 to the certain power, and the power number is given behind the e, right? Minus 15. So it's like 15 zeros in front of 1. Yeah, that's our conditional, right? That's our conditional. And now let's try to implement the updating formula, right? The first thing we need to update is actually x, right? Because we need to actually use x to update y, right? So here, in order to compute yn plus 1, we need to compute xn plus 1. And xn plus 1 needs to be computed from the previous value of x, right? That's xn. So x is going to equal to what? It's going to equal to what? Let's write the numerator first. It's 1 subtract the square root of what? 1 subtract x squared, right? That's the numerator. So it's all scalars here, so there's no matrix multiplication here. Everything is scalar, so the divider is supposed to be just a divide, right? But if you want to use dot divide, it's still going to give you the correct result. It's just not necessary to do this kind of element-wise division because everything is a scalar, right? And then what's going to be the denominator? It's 1 plus the square root of what? The square root of what? The square root of 1 subtract, again, x squared. Right? Right. So again, mathematically it doesn't make sense, right? But again, if you think about this equal sign as the assignment, which means that you want to replace the current value of x inside of the container with this particular value. How we actually computed this value? It's using the current value inside of the x container and this particular equation to compute the new value that's going to go into the x container, right? Once the new value of x container inside of the x container is being updated, is updated, we can use that to compute y now, right? So y is going to equal to what? Now, y is going to equal to the previous y times 1 plus the new x, right? Previous y times 1 plus x squared, right? Squared. Subtract, and then 2 to the n plus 1's power. 2 to the n plus 1. 2 to the n plus 1's power. Multiply with x, right? And what exactly is going to be n, right? N is supposed to start with 0. N is supposed to start with 0, right? So for the first iteration, it's going to be x 0 plus 1, that's x1, right? So so let me see if n is supposed to start with 0 or is it supposed to start with minus 1, right? So if n actually equals to 0, then it's going to give you x1, right? Yeah, n is supposed to start with 0, right? And then inside the loop, we're supposed to increase n by 1. Right. Let's give it a run and see if the result actually makes sense or not. If it doesn't, then we may want to go back to actually check if our n, the starting value of n is actually correct. Right. And the importance for here is that you should update x before you should update y. Right. The reason is because the new value of y is going to depend upon the new value of x. So if you put this line in front of this line, so if you evaluate this line first, if you write the code like that, Control X suppose, if you write the code like that, then the result is going to be incorrect. You're going to have a logical error. Right? Because when you actually execute this particular line, the x value, the value that's stored inside of the x container is still from the previous iteration. It's not the new value of x yet, right? But if you execute this line after this updating for x, then the value inside of the x is going to be the new value, right? It's the updated value for the current iteration, right? And then let's just disp number of iterations, and then num to str n, right? And then let's just execute it. What's going to be approximation to pi? So that's 4, right? That's 4 y4, right? Okay, right. So if we look at y, is that 1? What exactly is y exact? Okay, so for the significant digits that's displayed here, there's no difference at all, right? But if you want to look at a longer, if you want to look at numbers with more precision or more significant digits, you can do this thing, format long, right? Then you can display y and then display y exact. Then you're going to be able to see all the digits, right? So pretty much every digit displayed here is like identical, right? Except for the last digit, last significant digit. So y is the approximation gives you a 0, but the exact value gives you a 1, right? So and the last digit is supposed to be like 10 to the minus to like 15 positions after the floating point. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, that's the 15th digits after the floating point, right? And that's how we can actually use the while loop to make approximations to this irrational number pi, right? And by using this particular formula, we can get to the approximation very, very quickly. We can get a very accurate approximation very quickly, right? Just take like 4 iterations to reach it. Right? So it's probably a very important result in mathematics, right? When people first come up with this particular formula, they must be very excited because you can now sort of come up with a very fast algorithm that allows you to compute pi to a significant number of digits after the floating point. That's a tremendous tremendous achievement into the mathematics one. And here we're actually using it to demonstrate how to use the while loop, right? And the important thing here to remember is the updating formula, the sequence of the updating formula, right? The ordering, it's important. It's very, very important, right? And if you actually switch the order, let's do another calculation just by switching the order of these two lines, right? Let's just find out if it's still going to work. Right? Maybe it's going to work, maybe it's not. I'm not sure. I haven't tried it before. So it's 1024 iterations you get to pi, get to 1 pi. So you still can actually get to the approximation. It just requires a lot more iterations, right? Oh, y is not a number, so you didn't actually reach the and the y exact. Subtract the y. It's not a number, right? And when it actually reaches a not a number, then this conditional is still evaluated to false, right? So let's Control C, copy it, and then reproduce it in false. So 0 means false, right? So this conditional is still evaluated false, so it jumps out of the iteration. So if you switch the order of the two statements inside of the loop, you're gonna get an incorrect result, right? In fact, it's giving you a completely nonsense result, not a number, right? So the approximate value y is not a number, right? So it must have something that's 0 divided by 0, so it gives you this kind of result, right? What's going to be the value of x? And everything? X is 0, so it's 1 subtract 1, that's 0, divided by 1 plus what it's giving you. So if x is 0, right? So x is 0, then y equals to because the previous iteration of y, I think at a certain point the y becomes not a number, so all the rest of the iterations becomes just rerun it. But anyway, that's my point is that you have to pay special attention to the ordering, right, of the updating formulas. Right, Control X. Let me put it back. Right. And this code is actually correct. Right? If you switch the order of these two lines, it's gonna be a logical error. It's gonna give you an incorrect result. Okay, so next time let's try to look at what is the so-called function handles, and how do we actually use that to write our, and together with the while loop to solve our to solve our problem, right? Using Newton's method to find the root of a arbitrary function.